Well, this is going to be a hard one for you little chipmunks to work on, so make sure you focus. Okay, focus. So, the rate at which a drug disseminates into a bloodstream is governed by the ordinary differential equation, dx dt equals r minus k times x. By the way, x is the amount of drug in the bloodstream. And r and k are positive constants, and the function x of t describes the concentration of the blood in the bloodstream at time t after it's administered. So, find the limiting value of x of t as t grows large. That is, find what x of t would be as t goes to infinity, and at what time is the concentration half of that value. We make the assumption that at time 0 there's nothing in the bloodstream. Okay, certainly it's a first order linear differential equation. I don't think anyone would argue that, because if we just add the kx to both sides, there it is, and that can be solved with an integrating factor. See lesson 1 from unit, or lesson 7 from unit 1. Integrating factor will be e to the k dt. So that's e to the kt, and multiplying both sides by that, we got e to the kt times dx dt plus k times e to the kt times x equals r times e to the kt. And what happens is the left-hand side is the derivative of e to the kt times x. See, because it's first d second plus second d first equals r e to kt. So, derivative of this equals r e to the kt. Integrate both sides. We have a wonderful situation. E to the ktx equals r over k times e to the kt. Integrating e to the kt, you understand, is e to the kt divided by k. So r over k, e to the kt plus our constant of integration. To find x, divide both sides by e to the kt. Of course, on this side it cancels out. So we get x of t equals r over k plus some constant times e to the negative kt, since we divided by this. Well, now the question is, what is our constant of integration equal to? And we know in the beginning there's 0 here and 0 here, so r over k plus c equals 0, so c equals negative r over k. And that further refines our model. X at time t, the amount of concentration of the blood at time t, is r over k minus r over k times e to the negative kt. Going great. So, then another question says, well, what's the concentration in the blood as t grows very large? So let's go back and look at this. As t gets very large, this is, remember, k is positive, so this is e to a very large negative number. Well, all right, call it 0. So that means this whole part of the equation is just going to be 0, so x as t grows very large is going to be r over k. That's the limiting value. And finally it says, at what time is the concentration half of this value? So that's half of r over k, and so we just plug into our equation. Instead of x of t, we say a half of r over k, right? And then find out what the t is. So if we plug in half of r over k equals r over k minus r over k times e to the negative kt. Subtract r over k from both sides, we get negative a half r over k equals negative r over k e to the negative kt. Divide both sides by negative r over k. And we get a half equals e to the negative kt, so negative ln of 2, that's the ln of a half. If you want, it's ln of 1 minus ln of 2, but ln of 1 is 0, so it's negative ln of 2 equals negative kt, because if you do ln of e to the something, it's the something. So finally, we get the fact that it would take ln of 2 over k minutes to achieve half of the limiting value of the concentration. So, of course, we can't get an answer for that without knowing the k, but that is that, and I hope you're all able to. Yes.